Welcome to Star Talk, your place in the universe where science and pop culture collide. Star Talk begins right now. This is Star Talk. Neil deGrasse Tyson here, your personal astrophysicist, with my co-host Chuck Nice. Chucky baby.
Hey, what's happening, Neil?
All right, Chuck. You know what today is? It's a rare thing. We got to do this because I think people will want us to do it. This entire episode is a shameless plug for the very latest Star Talk book that is just coming out, and the reason why it's maybe it's not shameless, maybe it's full of shame. The point is, the title of the book is Cosmic Queries, and this is a Cosmic Queries edition of Star Talk. The book was inspired by this spinoff of the Star Talk flagship. And so I just want to celebrate that with all of our fan base and with you. And so I just thought I'd just put that out there, Chuck.
I love it.
So there's that. And it's published by National Geographic Books, who published the first Star Talk book.
That's right.
You know what the first Star Talk book was called, Chuck?
Let me hold on for a second.
The Star Talk book.
Yeah.
That's what it was called.
I'm looking at it over here. Wait a minute. It was called Star Talk.
The Star Talk book.
Yeah.
This one inspired by this spin-off branch of the Star Talk universe.
Right.
And so it's questions, 10 chapters, and each chapter is a really deep question that we barely have time to address given the nature of what we normally do in a Cosmic Queries. So what for this episode we're going to do, we're going to focus on chapters 3, 4, and 5.
Oh, wow.
Those are, how did the universe get to be this way? How old is the universe?
Oh, that's so impolite.
And and what's the universe made of?
Oh, sweet. We'll see what you
So
made of.
we had to reach uptown for our sort of cosmologist in the house, Jan 11. Jan, welcome back.
Hi, everybody.
To Star Talk. And you're published on on these topics. You got your own books, right? So first there's, together, Chuck, the Black Hole Blues. The Black Hole Blues.
I live for that. I live for that.
the Black Hole Blues. So you've got that book and a more recent one called the Black Hole Survivor's Guide, which is a very pocket-sized book and everything you needed to know to visit and not die in a black hole.
Right.
I think did I characterize that properly?
Yeah, exactly.
So clearly, black holes are one of the things in the universe. But could you just tell Jana, how do we get to be this way? What does it mean to have forces and matter and energy and space?
Yeah, universe. Why you gotta be like this?
Why you gotta be like that?
Why you gotta be like this, universe? I thought we were cool.
Oh my God.
I thought we should have.
I have a Star Talk book idea for you, though. You could write a book,
What's
a
that?
self-help book for like universes on how to be better. Like how to be a cooler, better,
How to be a better
more
universe.
actualized universe.
This is for the multiverse in us all, right?
A more actualized universe. That's awesome.
So I mean,
All right. So what's the basic? I can, as an astrophysicist, I can say we've got stars, galaxies, and planets.
Yeah.
But you look at it as a physicist at a much more sort of refined level, and I see things that gather according to forces. So what's been going on to give us the universe?
well, it's really interesting. You mentioned stars, galaxies, and planets, and those.
Oh my!
And those and those are things that actually.
Chuck has allowed one really bad program.
Well, they all.
Galaxies.
I'm a good audience. I laugh at all his jokes. I laugh at all.
Okay, that's very good.
So those are.
That's why you're my favorite guest.
And happy hour, buddy.
Oh, Jen, I didn't properly introduce you. You're a professor of astronomy and physics up at Barnard College. That's why I said we go up the street because you're just 2 miles north of the American Museum of Natural History, and you've been doing this since childhood, and it's just been great to have your enthusiasm. And plus, you hosted a PBS special.
Oh yeah,
but on black holes. What was the title of that?
Black Hole Apocalypse.
Black hole.
Yeah.
See what I'm saying?
Yeah, it's my.
You were the on-camera host of that Nova special.
One of my son's favorite.
That's so sweet. I held a little black hole in my hand. I got to do all kinds of cool CGI.
Yeah, crazy. But okay, go on.
Well, so you all the stuff that you listed stars, galaxies, planets are luminous objects, meaning they reflect or emit light. And that actually makes up much less of the universe, as you well know, than we used to believe. It's actually less than 5% of what's out there. I mean, if you think about everything anybody has ever seen or ever will see, makes up less than 5% of the universe. The universe is, in its volume, has dark energy permeating every part of space, and yet it is really should be called invisible, because it's not dark looking. It's literally invisible. We see right through it. And there's dark matter, and those have a huge
right. So
influence.
people will think, oh, dark matter, why isn't that just black holes?
Right.
But so there's a difference between matter you
way.
can't see
Yeah.
because it's not giving you light, and matter that you can never see because it will never give you light.
Yeah. There have
How
been,
would you distinguish that?
Yeah, no. It's a really good point. I mean, a black hole is really just a shadow. It just casts a shadow. And you have to illuminate behind it, around it, to notice the shadow, just like a tree doesn't make a shadow in the darkest night. So you need some light source to cast a shadow. So that a black hole is just absorbing that light and casting a shadow.
Janet, that's deep. I hadn't thought about that.
Yeah.
So
Black
you
holes
only know a tree's shadow is there because there's light surrounding the shadow.
That's right.
The shadow is the absence of the light.
Yeah, exactly.
The presence of the tree is the absence of the light.
The tree is absorbing some of the light, and that's casting a shadow.
If that shadow falls in the forest,
well, the thing,
then only the shadow knows. How's that? You got me? Are we good there? Okay.
So that's what people don't appreciate about black holes. That stepping into the event horizon of the black hole is just like stepping into the shadow of a tree. There's really nothing dramatic about it. You're just going into that region where the light is being absorbed, but it's a little trickier because the light can fall in behind you. But having said that, dark matter, which is what we were originally talking about, doesn't interact with the light at all. There's no shadow cast. There's no darkness. It just passes right through. So there's a cloud of dark matter, presumably, between me and my computer. Maybe not very much in the local universe, but
why
I see
do we
right
care
through
it's
it.
there? If it doesn't affect anything.
It affects gravity, right? So it interacts gravitationally. So there's a lot of it, and there's a big halo of it around our galaxy. So when we look at our galaxy, we think it's this kind of planar spiral, and it's so beautiful, and it's illuminated by all the stars. But really, there's this halo around it of dark matter, and we look right through the dark matter. And that halo affects the behavior of the galaxy, the evolution of the galaxy, and actually dominates the mass of the galaxy. So it's just, we're invisible to the dark matter too, you have to realize. It doesn't see us either. Dark matter, technically, if it had eyes, would look right through us too.
Wow, so this is a sci-fi story. Dark matter people coexisting with regular matter people. We would just walk through each other.
That's exactly what I've been talking about. I could be in the same body as a dark matter alien, and we wouldn't, because my gravitational field is so tiny, that we wouldn't notice.
And the molecules won't interact at all because that uses forces that dark matter doesn't respect.
Yeah.
There's a movie about that. It's so
There
cool
is. There's a movie waiting to happen in there.
Yeah.
Man. Okay, so, all right, so we got dark matter, dark energy, that's 95% of everything.
Mm-hmm.
And so...
So is it possible is it possible we're the anomaly? If 95% of everything
It's a really
is
good
the
question.
thing, if 95% of everything is the thing, is it possible that we are the anomaly? That we're
the thing.
Right.
Yeah.
We're not the thing.
It depends on how you look at it. The confusing thing about dark matter, we know examples of dark matter. We know neutrinos. Neutrinos exist. They emanate, for instance, from the sun, from thermonuclear reactions. They don't interact with light at all. They are technically invisible. So we know examples of dark matter. But we know that the neutrinos that we know about can't be the dark matter in the universe. We just can tell it's not heavy enough. It doesn't have all the right properties. So there's something like a neutrino.
So you're saying a neutrino is an example
of dark matter.
Of a physical object that doesn't really interact with us.
Only weakly.
Only very weakly. So this could be matter, if it's matter at all, that interacts even less.
That's right.
With less strength than a neutrino would.
That's right. Now,
Wow.
Chuck's question is like really interesting because it could just be the fact that there's so little of us. I mean, there should be none of us because you asked, why does the universe got to be this way? And it doesn't. We don't really know why there's a little bit excess, for instance, of matter than antimatter. And so it doesn't have to be this way. We're trying to figure out why it is this way. If there was equal amounts of matter and antimatter when the universe was created, there'd be none of us because we would just merge with our antimatter and annihilate. And there'd be nothing left but the dark stuff.
So some law of physics that we take as canon was broken.
Yeah.
Or violated in the early universe.
Yeah. And we still don't understand.
If matter always comes in matter-antimatter pairs,
yeah.
And we won that contest
right.
as this excess froth.
Right. Right.
And so you just declare that some rule got broken in the early universe? That sounds very like you don't know what's going on.
Well, that's true. We don't know what's going on, but sometimes
that's the end of the.
There you go.
So this is actually interesting.
Let's go have a beer. Yeah. We're done here.
We do know that there are slight matter-antimatter violations in the laws of physics. Why there are these tiny violations, we don't know. There's an example. The universe was created with a lot more matter in it, a lot more, and a lot more antimatter. It all just went away. And this little ashy residue was left of this little excess of matter, right? So that's what goes into us. So you can imagine.
Could you have a universe where, in fact, the matter and antimatter were strictly equal all the way down and still have a functioning universe? Maybe not with stuff in it, but would it be its own space, its own place? And could you have a universe that has just dark matter and dark energy in it and no regular matter?
You absolutely could have a universe. I mean, if you imagine the multiverse, which you made very quick reference to in the beginning, Neil, like if you keep kind of making universes like babies, they're all slightly different, right? Mm-hmm. They have a certain genetic code. We know it's still the underlying laws of physics, but maybe certain slight parameters can be seeded differently. And so maybe there's a universe that has no excess of matter over antimatter. And that really depends on whether or not it's absolutely fundamental to the laws of physics or it's something that got broken, like you said. You know, for instance, the universe is left-right symmetric. I don't expect it to be different on my left and my right? Because that doesn't even really matter. I can move around. The universe should be the same. But I know that in this room, it's not. I know that my microphone's on my left, and that's different. That's broken it just physically, even though the laws of physics should be the same on my left and right. I love the looks on your faces right now. For anyone who is just listening, I just got like 4 eyes.
Yeah, it's like, what the hell?
Well,
first of all, you had me at baby universes because my mind just started going off to all these other universes that were just like, you better take care of your kids.
You got too many kids.
You got too many kids.
Yeah, there could be a whole bunch of little baby universes out there, exactly. Some of which are you could say less successful on the basis of what we think is important, which is the emergence of sentient life.
Right.
And, you know, you're not going to make a lot of sentient life out of dark matter, presumably. Now, there could also be this thing where the dark matter sector has a whole reality. It makes stars and galaxies. We just can't see them. And it sees them and it has this whole other reality and we're just like in parallel. Completely invisible to each other. Dark galaxies, dark stars, dark planets. And
all right, so from what I've read, and I have a cursory understanding of this, I have like an evening news account of this. At different times from the early universe to today, matter, gravity, dark matter, dark energy all have different ways or different strengths of their capacity to manifest.
Mm-hmm. Yeah.
Okay. So who's dominating today?
So today we know that the overall energy density of the universe is dominated by dark energy. And exactly as you said, that was not true very, very far in the past. It's like a soup of ingredients that compete at different phases. And the dark energy, the strange thing about dark energy is as the universe expands, because the dark energy is everywhere, it's like it feels more of it. So the expansion gets a little faster, and then it feels even more of it. Because it's
embrace
just everywhere.
Your rage.
It doesn't dilute, right? Like if I took a hot gas and I expanded it, it would dilute and get weaker. Dark energy, and that's what happens to the primordial soup of matter in the early universe. It's really powerful. It's totally dense.
So we're diluting our
dilutes.
gravity. Mm-hmm. We're diluting our gravity and not diluting the dark energy.
Yeah. So that's right. The expansion is we're getting further and further away from other galaxies, so that's diluting their gravitational effect on us. But the dark energy is staying the same.
Okay, so you compare the two. the dark energy systematically wins out.
Eventually it'll win. Even if in the beginning, not necessarily the galaxy, but like the stuff dominated. And then the universe was expanding and it got more and more dilute and weaker and weaker. And then the dark energy, there it was. And it just took over.
So dark energy feeds off the vacuum of an expanding universe.
It might be the energy of the vacuum of the expanding universe. So the more vacuum you get, the more energy from the vacuum you get.
Weirdly, that reminds me of the Weeping Angels episode of Doctor Who, where Weeping Angels, they feed off of your life energy. And you disappear out of your time and you show up in the past because they took your present life energy from you. So dark energy is taking whatever we possibly had left of ourselves.
It's a cosmic vampire.
It's a vampire. That's what it's doing.
If it keeps going like this, a friend of mine used to say, we have to do astronomy now. Because eventually in the far future, there will be no galaxies in view anymore. They'll all be too far away for us to see.
There'll be no cosmology. We'll just see our galaxy and the rest of the sky will be empty. Imagine astronomy under those circumstances. We'd never know that there was anything outside of our galaxy. Well, that's what it was until 1920. Until 1920, no one had any idea that the fuzzy objects were galaxies. It was just the solar system and the stars in the night sky. Yeah. And that was the universe. In fact, that was the universe to Einstein. There was no understanding of a Big Bang or anything else. And
that's
so
right.
It was just, no, in fact, who's the guy who first advanced the Big Bang? The monk or the priest?
Lemaitre?
Lemaitre. The Belgian priest, right? Yes. Who really put the math behind Einstein's equations. Did he by then have Hubble's expanding universe? He must have, I think.
So Friedman and Lemaitre and some of these, and Robertson and Walker, there were a bunch of cosmologists that were thinking about this long before actually Hubble. And Einstein thought they were wrong. So Einstein publishes his theory, but he doesn't know that there's a Big Bang. It's not like it just hits you in the face. You gotta study the mechanics of the theory. And so people jumped in even before he did, and they realized, oh, this is really strange. If you imagine a universe dominated by matter, they didn't even know about dark matter, but just stuff, it actually wants to expand. It's actually hard. That universe doesn't want to just stay static. It's actually really, really hard to make it static. So I guess what
I'm thinking is they're imagining an expanding universe before they even knew anything about galaxies.
That's right.
They're just thinking about stars in the night sky.
They were just imagining
the universe.
Yeah, they were just imagining like a hot stuff everywhere. Just pretend. It was kind of pretend.
So without galaxies, we have no knowledge of an origin of the universe. And we'd be dumb stupid. Yeah, so we have to do astronomy now.
Yeah.
Because one day we're going back to that same state.
Yes.
But only because those galaxies won't be observable.
At all, right.
At all. So it'll be, somebody will be like, son, believe it or not, there was a time where people looked up into the sky. and they thought that they saw things, son.
Oh, Grandpa Chuck, tell me more when you were a child.
Yeah.
Believe it or not, son, they used to look up there and see things, but no longer.
It's true. Basically, most of the evidence that we had a Big Bang in our past will eventually just fade away.
So Jana, before we take a break and then get to our actual cosmic queries with people's questions, I lose sleep at night wondering whether we today live in a time where an entire chapter of data has been removed from our awareness, just as it will be in the day when there are no galaxies.
Indeed.
In a post-apocalyptic civilization, they will know nothing of Chuck's stories about the day gone by, and they will try to figure out the universe with what they've got.
Yeah.
So what chapters are we missing today, thinking we have full access to all the data, yet we don't?
And that's funny because I lose sleep because I normally drink vodka before bedtime.
We've got different reasons for losing sleep. Okay.
We should have little shots for our like if you get the cosmic query wrong. So
So, Jana, you don't worry about whether we're missing something?
I totally do, but I think this is a really interesting question because people say things like, if there's no way to observe the multiverse, then it's not a scientific question. I think that's false For instance, in the far future, if people say there's no way to observe other galaxies and I don't know why, and one person pontificates, maybe it's because the universe was expanding so rapidly that they're now beyond our view, they'd be right, but it's technically untestable for them.
Right.
So I do think it's a scientific question, even if you can't resolve it observationally. So yeah, there are things like if the universe has extra spatial dimensions and right now they're really small and we're really big, maybe that's something we can't test right now, but maybe in the far, far past it was technically testable.
Wait, so Chuck, she's saying one day a new dimension is going to grow out the side of your body. That's what
believe me, since the pandemic, that has already happened.
Mercifully, we're all like filmed from here up.
Chuck has 6 legs and 5. we got to take a quick break. When we come back, Jana, you're here for us.
Yeah.
We're going to take questions from our Patreon members when Star Talk returns.
I'm Joel Cherico, and I make pottery. You can see my pottery on my website, cosmicmugs.com. Cosmic Mugs, art that lets you taste the universe every day. And I support Star Talk on Patreon. This is Star Talk with Neil deGrasse Tyson.
We're back. Star Talk. Cosmic Queries. This is a celebration of the release of the second Star Talk book called Cosmic Queries, inspired by this spinoff of our show, one of our more popular formats of the Star Talk portfolio. And Chuck, I got you here for this, of course.
That's right.
And we're doing chapters 3, 4, and 5. And I got their titles written here. How did the universe get to be this way? How old is the universe? And what's the universe made of? And Chuck, you've been collecting questions. Let me just lead off. Jana, I've heard people say the universe is designed just for us, okay? Just so that we can have life. But that seems really inefficient if life as we care about it, human life, has been around only for a couple 100,000 years, and the universe has been around for 14 billion. That just seems really inefficient. So if you want to say, everything's set up for us, that's a pretty big waste of time and space.
Yeah, especially if we're just here to make plastics for a little while and then we're going to go on and leave the plastic behind,
The plastic will survive us.
Yeah, it's like a George Carlin skit. He's like, the planet just wanted us to make plastic for it and then be gone.
Right.
Because there's no known thing that dissolves plastic, right?
Yeah,
right.
Not yet.
So Chuck, give me some questions, dude.
All right, here we go. Let's
all from Patreon.
Everybody's from Patreon, and this is Richie Damani. Richie Damani says, firstly, Jana, Neil, Chuck, thanks for taking my question. So we know about the LHC at CERN, which has made huge discoveries in particle physics. But do you have any knowledge of a larger project that is in consideration that will further our knowledge of the quantum world?
Yeah, Jana, is there another particle that people think is out there, and now we need something bigger than the Large Hadron Collider to find it?
Well, dark matter. So the Large Hadron Collider has been very successful. It's very exciting. It discovered the Higgs particle, which explains why anything has mass.
Did you say Higgs particle or Higgs particle?
Higgs.
I thought you said the Higgs particle.
The Higgs particle is a little different. The Higgs particle explains why you eat possum.
Very, very culturally insensitive. Yeah.
Yes, exactly. Just the Higgs particle is just like, I believe I'm on a quantum level. Y'all.
Barbecue that possum. All right.
Well, so, it's called the God particle in sort of colloquially, but it was originally called the Goddamn Particle by Leon Letterman, the Nobel Prize winner. He wanted to call his book The Goddamn Particle because they hadn't found it yet. And his publisher made him change it to the God Particle, which he said ended up alienating 2 groups, those that believed in God and those that didn't. So it's since stuck. Quote. It's since stuck. Yeah. But the LHC could have detected dark matter, and that would have been really that would have just been what everybody had mostly hoped for, and it hasn't. So could we go higher energy and higher energy? If you think of the energy of the Large Hadron Collider, it's from a very early era in the universe's history, and you'd expect to be able to make kind of everything. The earlier back you go, the more you can make, more kinds of particles you can make.
I never thought of it that way. You're telling me the LHC is a kitchen.
Yeah.
It's a cosmic kitchen. And so if whatever energy you hit, you just look on your cosmic scale and say, I got you back to 3 seconds in the Big Bang.
Exactly.
And then higher energy, I got you back to 1.5 seconds.
Yeah.
So how much more energy are you going to need to get to the formation of dark matter in the early universe?
Like 10 million times higher.
Oh, okay,
Wow.
Chuck.
That's all.
That's all in the collection. Yeah, we got that.
That's not a problem, right?
And so that's really high.
1.22 gigawatts of energy.
That's what we need.
Now, like, here's what's going on.
1.21 gigawatts.
And we're going back in time, too. So, yeah.
So in the recipe book that Neil's looking at that tells you if I cook at this temperature, I'm going to have this number of particles, that's just based on as much as we understand. And as much as we understand, between the energy of the Large Hadron Collider and the very, very, the earliest second of the big tiniest little fraction of a second of the Big Bang is like 10 million higher in energy, but it doesn't mean we're right. So there could be like a bunch of stuff that starts to appear that we had no idea about. And that's what everybody, other stuff, not just like dark matter might appear in there. And other stuff maybe dark matter isn't alone. Maybe there's like a whole dark sector, a whole dark reality, and we start to discover tons of dark matter particles and forces, dark forces.
So, Jenna, I love this. You're saying a more powerful collider could just open up a whole new door to what's going on in the universe.
Yeah.
Cooking with particles. Oh, dear. Yeah.
Now, we do know that we will never hit certain scales with usual technology. Like, you would have to have all the resources in the solar system in a particle collider the size of the solar system. So that's why we do astronomy.
You need 1.21 gigawatts of power.
I think that's the benefit of astronomy, is that stuff happens at higher energy scales than human beings can engineer. And so we know we have high energy particles hitting our atmosphere from supernova explosions or solar systems that are at higher energies than the Hadron Collider.
So the universe is a better Hadron Collider than our Large Hadron Collider.
That's right. It just requires, it's harder. You can't manipulate it. You can't force it.
You just have to wait.
You
have to wait until it makes what you want. Right.
Yeah.
Exactly.
The particle bites you in the ass. It's okay, I guess you exist.
Yeah.
It's basically like being an actor. Don't call us. we'll call you.
Right. Exactly. Just got to wait for it to roll up.
All right. So that's good. I like that. And so, but I want to emphasize a point you made before we go to the next question. What you're saying is, in our life experience, if something lasts 3 minutes or 5 seconds or 1 second, that's not very much time, and who cares about the difference? But in the early universe, there are things that lasted a trillionth of a second, and then a quadrillionth of a second. And we say, oh, that's just less than a second. But each of those are huge differences in the energetics of the early universe. Is that a fair way to think about it?
Absolutely. I mean, there's stuff that can be created in the first, trillionth of a trillionth of a trillionth of a second that very quickly decay away into other stuff and will never be made again. Because the energy scale required to create a single particle with that mass, even though the mass itself is objectively not a lot compared to, a coffee cup, it's a lot for one particle. And it will never be made again, probably in the history of the universe.
Wow.
So anything that was born in the first trillionth of a second and dies a trillionth of a second later, lived for a trillion of its own lifetimes.
Yeah. That was a full life.
Right. Man.
That was its life expectancy.
Wow.
Yeah.
Look at that. Okay.
So we do think you could make, in fact, it's possible that one of the heaviest single particles that ever could be made is a microscopic black hole. And that it was made not by dead stars, not by collapsing matter, but it was made as like a quantum particle in the very early universe. And that it was the weight of like a little pile of flour, but it was incredibly smaller than a nucleus. So it's
very
tiny.
dense, so dense to be a black hole. It's black hole dense.
Exactly. It's very spatially tiny, but heavy for its incredibly small spatial size.
And if I lost my keys into a microscopic black hole,
Yeah, don't reach in to pull them out because that ain't gonna work. Okay.
Could I get them back?
Don't do that.
Well, Chuck, I'll get you another pair of keys, another set of keys.
That's
for what
like
you're going in.
chapter 3 in Black Hole Survival Guide.
Sweet.
So, you know what this reminds me of, Jana? I forgot which book, forgive me, but the novelist Kurt Vonnegut, one of his novels, he says, this is the last sentence ever spoken by humankind. It was one scientist speaking to the other and says, let's try it the other way. That's the end of all civilization.
Right.
So it's like, let's see if we can make a mini black hole. Last word ever spoken.
Well, so there was some discussion, serious discussion about whether or not the Large Hadron Collider could make one of these. And
a mini black hole.
A mini black hole. And we usually think, no, you really couldn't until you were at the much, much, much higher energy. But it does turn out that the universe does have extra spatial dimensions and they're of a certain size. You could actually manipulate the strength of gravity. If you think about it, gravity dilutes when you have more dimensions, like more volume, it gets more dilute. So if these dimensions, you start to notice it brings the scale of making black holes down in energy. Because gravity's getting, it's getting into your range because of these extra dimensions.
Wait, so what you're saying is if you have extra dimensions, then the gravity has more space to dilute into.
Yeah.
But that means that your thresholds of gravity, bad stuff is lower.
Is lower. So you might make a black hole at the Large Hadron Collider if that's the case. And so there were injunctions taken out by people to try to stop the Large Hadron Collider from turning on. Because there was this anxiety, well, if you're going to make a black hole, it's going to like digest, it's going to consume the Earth and
Gonna kill us all.
Yeah.
Right.
But the argument, which might not be very soothing because it is theoretical, is that they would evaporate too quickly. They would just go off like firecrackers.
So you're saying you would possibly make them and they would consume the Earth, except that Hawking radiation protects us.
That's right. And black holes are not as dangerous as people portray. There's a black hole in the center of our galaxy. We orbit that black hole. It dominates the entire behavior of the galaxy. And it's not a vacuum cleaner, right?
Chuck says the person who wrote the book, Black Hole Survival Guide.
Right.
No one writes a book.
If you want to survive, just stay here, basically.
Yeah. No one writes the book, The Puppy Survival Guide. No, you write survival guides with stuff that's going to eat you. Okay.
Yeah.
That's funny.
There's the Kitten Survival Guide. No, Black Hole Survival Guide.
Explorer's Peril. Yeah.
All right. We got to take a quick break. When we come back, more Cosmic Queries when Star Talk returns.
Time to acknowledge our Patreon patrons that make this show possible. Sunny Day, Shane Dolakia, and Penny Joy. Guys, thanks so much for your support. What would we do without you? Well, we probably wouldn't make a show this good. And for anybody listening who would like their very own Patreon shout out, please go to patreon.com/StarTalkRadio and support us.
We're back. Star Talk Cosmic Queries. We are celebrating the release of the second Star Talk book, Cosmic Queries, inspired by this format. By the way, we're going to have different guests for the different kinds of chapters that are in the book. And right now, we've got some very deep questions about what's the universe made of and how did the universe get to be this way. Jana Levin, always good to have you.
Always
You're
fun
a good
to be
friend of
here.
the show. And by the way, that place behind you,
Oh, yeah.
it looks like a bunker,
I
but
know.
but it looks like a chill place to never be found. So where are you right now?
So I am also director of sciences at a cultural center in Brooklyn called Pioneer Works, which is largely originated in the arts. And I've been doing science events here and bringing science into the community. It's very much an attempt
That is just so Brooklyn cool. I'm jealous.
I have to say, this is what I love about this place. It's free and it's open to all, and it's a donation only model. And we really bring like amazing people here to talk about science, to talk about art, to have exhibitions. And it's really important to us that the doors are open for everybody.
And the intersection between science and art is much greater than anyone ever thinks about or imagines. And you're there in the middle of that. So keep up the good work. All right, so Chuck, give me some questions for our cosmologist in the house, Jan.
Here we go. Tovi Sonnenberg says, hey, Dr. Tyson and Dr. Levin, sometimes physicists say that the existence of a particle, such as the axion, is predicted by a theory or completes a theory. What do they mean by this?
Ooh, good question.
Well, that's okay. So you know what the best example of that is the Higgs, which we already mentioned. So we looked at the standard model of all the matter in the universe, and there was just like one thing missing because we couldn't make sense of why particles had masses, essentially, unless the Higgs was proposed. So what the Higgs does, it's basically, again, it permeates.
But Higgs was a person.
Higgs was a person who proposed the theory. Uh-huh. And the idea of the Higgs particle was that there was this field that permeated all of space, kind of like what we think about dark energy. So some people wondered if dark energy itself was like the Higgs permeating all of space, but the numbers didn't quite work out. But it could be something like that, dark energy. It could be something like this field that permeates all of space. And as we move through this field, because of our interactions with the Higgs, it creates a kind of inertia. We get sticky, we get gluey. It's like viscous moving through it. And that's what gives us mass, right? Mass means I'm harder to push around than a thimble, but I'm less hard to push around than a car. There's inertia. And this difficulty pushing around has to do with our interaction through the field. That's the idea.
So the Higgs particle was filling a gap. So that's right. Different from discovering a particle that nobody ordered.
That's true. So like Robbie said, it's a great quote. The physicist Robbie said, who ordered that when he began to discover more particles? So the Higgs was predicted to fill a gap, which is exactly what the question was about. And lo and behold, there it was.
This can make all you all very proud of yourselves, right? Because it means you understand not only the physics that we've discovered, but the physics awaiting to be discovered. That gives you pretty good confidence there.
That's the best. Although I have to say, everyone really hoped that something like the Large Hadron Collider would discover something we had never predicted. But people don't understand about physicists. We don't want to wrap it all up in a bow and be done. We want more. And so it would have been incredibly exciting if they had discovered something that nobody had ordered.
So
it would have given a lot of people work.
Steeped in ignorance.
We look forward to the questions. The questions are the fun part. In fact, Robbie, who you're quoting, his mother used to say to him, did you ask a good question today? You know.
Ooh, I like that.
Not did you learn something?
Basically, you guys are just never satisfied, is what you really say.
That's right.
It's a weird job. Like, the more questions you answer, you're getting yourself out of work.
Sweet. Sweet.
Okay, you want job security. All right, there it goes. All right, let's keep it going. Let's do a lead in up to a lightning round. So let's do a little faster, and then we'll pick up the pace and see how far we can get.
Well, that's a perfect segue into John Schwalbach's question, because John says this. Hi, Jana. Please tell me, what is string theory in 2 sentences?
He wants it in 2 sentences.
There you go.
Okay.
So he's right on time.
Okay, go for it.
String theory is actually so compelling because it can be summarized in 2 sentences. When we look at the microscopic universe, we used to think we saw little fundamental particles. It's possible that if we zoom in on those fundamental particles, all of which are different, there's a lot of them, quarks and electrons, that when we zoom in, we realize that they're each tiny loops of string, the same kind of string, and they're playing different harmonics on the string to express as a different particle. Mm-hmm. So an electron is simply ringing at a different note than a quark. But they are fundamentally the same. That was more than 2 sentences, but it was fast.
That was good.
That was good. Listen.
That was good. So you're saying everything in the universe could be made up of strings?
That's right. Even light, photons, even the Higgs, everything
How
would
about
be...
dark matter?
All of it would be the same fundamental string playing different notes.
Wow.
So the string could be playing notes that we can't detect, such as dark matter, dark energy.
That's right.
Mm-hmm. That we can't see.
Right. So we think of particles as just their identity in terms of whether they interact in certain ways. And so all of those features, it's like a short list of numbers, are harmonics on the string.
So the universe is nothing more than one big version of Name That Tune.
And this is the one we're in. We're in this tune.
We're stuck in this one.
We're stuck. We got this one going.
All right, give me another one.
Yeah.
Short answer, Jana.
That's so funny.
Best short answer ever.
If somebody else is able to observe us, but we can't observe them, could you imagine? They'd be like, God, what a shitty song. All right. So this is Woody. Woody says, is a quantum vacuum possible in intergalactic space or anywhere else? And would an area of absolute nothing be a hole in space-time? So if you can actually get to nothing, did you punch a hole in space-time?
Well, there's a lot of stuff going on there, but the quantum aspect is the most important. To some extent, you can never have a quantum completely vacuum, nothing. You can't have a complete quantum vacuum. And that's because of the Heisenberg uncertainty principle says, I can't ever really precisely state that a particle is there or not there. It means I can't say nothing exists because I have the same uncertainty. There's an uncertainty for things to exist.
Listen, let me
gotta be easy on Chuck. Gotta be easy on Chuck.
Now.
Chuck had a hard night last night.
Yeah, exactly.
You're laying this on him now.
Woo, I drank last night. You should let me know. Dang.
Oh, yeah. So, to say there's nothing means you have zero uncertainty that there's nothing.
Right.
And you cannot have that at the quantum level. It doesn't exist. It's not just that there's a problem with the human knowledge. There is no meaning to saying it's exactly precisely empty.
So you're saying that nothing can't exist is basically what you're saying. There can't be a nothing.
No. It's
not that there can't be a nothing.
Nothing
you cannot be sure that there's nothing.
Well, nothing isn't quite as empty as you might imagine.
Right, exactly.
The most nothing
is something.
It might be, so this is why people talk about the dark energy as being the energy of the vacuum. The most nothing you might be able to get is this kind of frothy quantum things, a cloud of possibilities. And that has an energy associated with it. And you can calculate the energy associated with it. And so far we keep getting the number wrong. If I look at quantum mechanics as I understand it and I calculate the energy of the vacuum, I either get zero or I get something absolutely enormous. What I don't get is dark energy. So you could say dark energy is not mysterious. What's mysterious is why it's so low, why it's either not zero or huge. And that's what the real mystery is how do we make the energy of the vacuum tuned just to where what we observe? And nobody knows how to do that.
All right. I cry foul here. So what you are taking as a given that everything you're describing is happening in the space-time that we've come to know and love. But back to the person's question, if you did find a place where the quantum laws don't apply, have you opened up a rip in the very fabric of space-time where possibly other rules of quantum behavior apply?
Well,
or no rules at all?
Yeah, I would say that to do such violence as to have a hole in space-time. So you have to think of space-time as being formed, responding flexibly to matter and energy. And so you can't make a hole without having tremendous other phenomenon going on. We know what the solution would be. It would be nice, smooth, empty space-time. So you make a hole by doing something like a black hole, like doing some real intense violence with energy and matter to create that hole. So I would say maybe closer answer to our listener's question is that it might be quite the other way around, that quantum mechanics creates space-time. And that is a new idea that's been people have been flirting with maybe for decades, but that it's not that you have these two separate things, gravity, space-time, quantum. It's that things like a black hole emerge from the quantum phenomena and not the other way around. So you don't even have space-time unless you have quantum mechanics.
I get it. So you can't even pose the question, what happens if there's no...
Exactly.
You can't separate the existence of space-time from the quantum phenomena
If
that
that's-
operate within it.
Exactly.
If it's
If that's
created.
true.
Created it in the first place.
If that's true.
right.
So one way to think of it is like embroidery. So embroidery, like let's say you're embroidering something, each thread is like a quantum phenomena. And from far away, it might look like a black hole. But on closer inspection, you realize it's a bunch of intertangled quantum threads.
Right.
Exactly.
Wow, that's cool. That's a really cool concept.
It's pretty cool.
All right, okay.
I'm
We gotta
just
go
saying,
full up what?
I can't wait to go to a party with a bunch of theoretical physics and do whatever drugs they are doing.
We'll sign you up, Chuck.
Exactly.
All right,
Okay.
so fast lightning round. Let's do it.
Okay, here we go. My name is pronounced Frederick. If the universe with everything expands, does that mean that quarks grow too, or is it just the space between them?
Very
Okay.
good question. So
Very good question.
Lightning round, go.
Yeah, here I am in Brooklyn. Brooklyn is not expanding. Famous reference to Annie Hall. So locally, I'm bound to the Earth. I'm not expanding with the expansion of the universe because locally, the Earth is more important to me. Also, my atoms are bound together by different forces, and they're stronger than the expansion rate of the universe. Presently, I'm not being torn apart. If that's maintained in the future remains to be understood. It might be that the expansion gets faster and faster, and eventually, indeed, Brooklyn begins to expand. And that's just something we don't know about the fate of the universe.
And in fact, the final chapter of the Cosmic Queries book takes you there. It
Great
looks
Rip.
at the Great Rip, the runaway, where not only does everything get ripped apart from everything else, the very structure of particle matter itself breaks apart. It can't even hold itself together. And that scared me. I lost sleep that night.
It doesn't scare me. I've been in that position many times in my life. Where I just can't hold myself together.
You can't hold yourself together.
Just can't hold myself together.
Chuck, we're actually out of time, but I want to get one more question in here. See if you can
All
squeeze it in.
right. Hey, Jana. Hey, Neil. I love you both. Big fan for a long time. And thank you both for instilling me with a cosmic perspective. In our universe, we observe virtual particles that pop in and out of existence. Could this phenomena be compared to that of a 3D object passing through a 2D flatland?
I love that.
It's very interesting. Well, it is possible. So I said string theory. I only had 2 sentences, which I already overused, but it is possible that there aren't just strings, but there are membranes, higher dimensional surfaces. And so imagine, so we started with particles, points, and then we went to strings, one-dimensional objects. Now maybe there's like a membrane, a 2-dimensional object, and maybe there's higher dimensional objects as high as you can fit in the higher dimensional space-time. So one of the ideas is imagine we live on like a 3-dimensional membrane, and when we see a point particle, it's really the endpoint of a string stuck to our membrane. It's not exactly the question asked. But it's
No.
related.
But it is the
related.
intersection of dimensions.
That's
That's
so
right.
cool, though. Yeah.
So that I see a point particle moving around in my space-time because I can't see that it's really connected by a string to somewhere else. And also imagine how that allows for what would appear as an illusion to be faster than light travel.
Right.
Because I could have this thing that's actually connected and it's doing something, synced up, but that's because it's fundamentally connected and I don't realize
That's
it.
amazing.
Wow.
So it's like having the point of a pencil down on the paper,
That's right.
and the point is what I'm seeing on the
Exactly.
paper. But then there's a whole
pencil.
Yeah.
connected to that point.
Yeah.
That,
Exactly.
That's some freaky stuff, man.
Yeah.
That's Freaky Friday
and so
stuff.
when we
Okay.
calculate the energy of the vacuum and try to find the dark energy, we have to calculate all of these kinds of objects that might be in the universe and what they're contributing in their quantum energy to the vacuum.
Wow. Damn.
We got to close it there. I'm not going to sleep for 3 days. Janet, thanks for showing us your digs, the
Yeah.
Pioneer Works. And Chuck, you tweet at Chuck Nice Comic.
Yes,
Always good to find you there.
Thank you, sir, for saying it. I just love that Jana has Pioneer Works. It's like, and Jana, we see your Pioneer Works, your swan song accomplishment to science, and Chuck,
tweets.
you tweet, right? You're on Twitter, right? You're on
I
Twitter.
love it.
Chuck's on Twitter. Okay, fine.
Oh, snap.
All right. So we just encourage you to check out Cosmic Queries, the second Star Talk book, National Geographic Press. I'm Neil deGrasse Tyson, your personal astrophysicist. And of course, I bid you to keep looking up.